Still being here and still being awake. You guys are awesome. Nobody has actually slept away. I didn't hear any snoring so far. And a 5-day intense short course like this is not easy to handle. So good job everyone. We are almost there. So in this tutorial, I want to talk about temperature measurement. We have been talking quite a lot about experiments, and so I think it makes good sense for me to discuss how do we measure temperature. Of course, this is in the context of lithium-ion batteries, but what I will talk about is very broad, and temperature can be and needs to be measured in a wide variety of devices. Okay, so the first question is, how do we measure temperature? What are the different techniques to measure temperature? Can we make a list? Can each one of you maybe contribute one way to measure temperature? Thermocouple, okay. So let's say thermocouples. What else? Keep shooting, please. Anyone? Thermometer. The word thermometer means a device that measures temperature. So I want you to be a little more specific. Expansion, sure. So I will say expansion based. Maybe I can redefine my list. I am asking you, what are the different ways in which temperature can be measured? So this is by measuring a potential difference due to temperature. This is by measuring expansion because of temperature. What other effects can be used to measure temperature? Change in what? Sorry, length? That is expansion. How about change in resistance? How else will I measure temperature? I have a body. I have this. Heat exchange is a very good one. If I have something and I want to measure its temperature, I have nothing else in the world, what will I do? I have only myself. I will touch it, right? I will touch it and I will feel, does it feel hot or does it feel cold? So actually touch itself, sort of a biological way of measuring temperature. Something happens to my cells when I touch them to a hot body or a cold body, which allows my mind to sense temperature, right? And it turns out that biological sensing is actually very good. People have done measurements in which they took fish and put it in a tank where the temperature changes from one end to the other. The fish all congregated to one particular temperature where they were most comfortable with an accuracy of about 0.1 degrees Celsius. So that's very remarkable. Okay. By the way, our sense of touch in terms of measuring temperature can be very misleading. Imagine in this room I have this doorknob. If right next to it there was a doorknob made up of wood and I touch both of them, which one would feel cold? Huh? The metal one, right? Floors. If I have a tiled floor versus a wooden floor and I walk on, without shoes and socks, it feels very different, even if they are at the same temperature, right? These two knobs are at the same temperature, but the metal one feels colder. It is because when I touch something, my body is at 37 degrees Celsius, this is at 25 degrees Celsius. That temperature difference causes a flow of heat. My hand begins to lose heat. And my body does not measure temperature. It measures that loss of heat. It senses that I'm starting to lose heat from my fingers. This body must be very cold. Unfortunately, how much heat I lose is not only a function of the temperature difference, but also the properties of this body. It's called effusivity. Effusivity of metal is different from that of wood. That is why that is different. Anyway, what are some other techniques with which I could measure temperature? Huh? Change in pressure? Yeah, sure, why not? Change in pressure. How would that measurement technique look like? What would a pressure-based temperature sensor look like? It would simply be a cylinder filled with some gas, a fixed volume cylinder, right? With a pressure measurement device. As I take it here and there, if the pressure in this cylinder changes, then I will know that the temperature has changed. Provided two things, the volume is the same and it is an ideal gas. Because for an ideal gas, we know PV equals nRT, volume is the same, the mass is the same, pressure is in fact proportional to temperature. Right? I can easily see how the temperature changes because of changes in pressure. What else? Maybe one more item? Huh? Optical, yes. So changes in optical behavior. You will see here, thermocouples is changes in voltage. You will see here that in each case, we are not measuring temperature directly. We are measuring the change in something else because of the change in temperature. It's an indirect measurement of temperature. I don't think anybody really measures temperature directly. We all measure something else that changes because of the change in temperature. Yeah? Question? Comment? Okay. So in today's brief lecture, I want to talk about a few of these techniques, but more importantly, I want to talk about what constitutes a good measurement. In the previous lectures, remember I had said that I don't want to say that the temperature of this body is 35.2 degrees C. I want to say it is 35.2 degrees C plus or minus 0.2 degrees C. This quantity, which is called the uncertainty, communicates that, look, I have measured it to be 35.2, but it could very well be plus 0.2 or minus 0.2 of that. Where does this number come from is something that I want to think about. If I measure a temperature of 35 degrees C, is it really 35 degrees C, or could it be off by 0.1, or could it be off by 1 degree C? How much of an effort do I need to make to measure temperature with an accuracy of 0.1 instead of 1 degree Celsius? There are some scenarios in which measuring temperature with an accuracy of plus or minus 1 degree C is acceptable. Right? Can you think of a scenario where plus or minus 1 degree C is okay? Building ventilation, 1 degree C is quite okay, you know. Whether the temperature of this room is 25 or 24 doesn't matter to me. Right? In fact, most devices measure temperature or report temperature to plus or minus 0.5, I think. Right? And in the US, where we work in the Fahrenheit scale, the accuracy there is 1 degree Fahrenheit. Yes, and half a degree Celsius temperature change is roughly 1 degree F temperature change. But there are some other applications in which I want this to be much more accurate. If I am designing a spacecraft going into space and it's a really delicate experiment, it is not enough for me to measure it to plus or minus 1 degree C. It needs to be a lot more accurate. So let's think about these issues and how do I design an experiment in an effective way in order to get good confidence in my measurements. And for that, the example that I will take is that of a resistor. So here is a resistor R0, metal resistor. Okay, keep in mind not the colorful resistors that you see in electrical labs. Those are carbon-based resistors, and they have been designed to be temperature insensitive, because they want to put them on a device and then in a car perhaps, and as the car goes around, you don't want those resistances to change with temperature, right? those resistors, the colorful, cylindrical, tiny little resistors are not good temperature sensors because their resistance is not going to change with temperature. Instead, I'm looking for something for which there is a significant change in resistance as a function of temperature. In other words, if I was to plot resistance versus temperature, if I have one resistor that looks like this, that's a poor temperature sensor. You see what I'm saying? That one is a poor temperature sensor. I would like to see something like this. I would like to see a linear increase in resistance with temperature. I don't want it to be non-linear either. A plot like this is not desirable either, because after some point the resistance will go up so much that I may not even be able to measure it. Even a 1 degree Celsius change in temperature and the whole thing shoots off. This is the ideal temperature sensor for me. So if you go to a shop, and online usually these days, and you have several candidates, you've got to make a good decision about what is a good temperature sensor for you. Okay? Then beyond that, suppose I go and purchase this temperature sensor. It looks like a thin sheet with 2 wires coming out, and I attach it to the surface of interest. What do I do next in order to measure temperature of that surface? Tell me. This surface is getting hot, and I am interested in measuring the temperature of this surface based on this resistor. What's the next step I should take? Let's attach it. So, and we have discussed this at great length previously. How do I attach it itself is an important question. Yes. Where to? Exactly. And how to attach? Do I just put it there and press it with my fingers? Or do I put some epoxy between them and attach it? Thermally conducting, but electrically non-conducting. Exactly. So you can't use a metal paste or whatever which will short things around, right? Then what do I do? How, let's take a step back. How are we proposing to measure this temperature? By change in resistance. So I must measure the resistance of this body, and that will tell me the temperature of this body, right? That itself is not straightforward. How will I measure resistance? Can somebody propose to me a way to measure the resistance of this sensor? Fair enough. In order to measure a resistance, I must measure. Exactly. Yes, absolutely. Yes. So, sure, yes. So, our original task of measuring a temperature was sort of subcontracted to measuring resistance, which has now further subcontracted it to measuring voltage, right? So, I need a current source and then I need to attach a voltmeter in order to measure that voltage. How much current should we send through this thing?
It should be minimum, and that resistor should be highly sensitive.
It should be?
It should withstand the DC current.
Yes, yes. No AC. Let's stay away from AC. We'll send a DC current, and the question is how much DC current, and one comment was minimum possible.
Minimum possible, but and the resistor which we are using, it should be highly sensitive towards the.
Sure. So the sensitivity of the resistor is usually measured in terms of this alpha term, where alpha is the temperature coefficient of resistivity, right? Alpha should be as large as possible. So if for a certain delta T, delta R is alpha R naught delta T, right? And if this is my change in resistance, the change in voltage will be how much? It will be I times the change in resistance, and that would be alpha I R naught delta T. When I design this experiment, should my delta V be large or small? Delta V. Suppose I am trying to measure a change in temperature of 0.1 degrees C. I am ambitious here. I want to measure a change in 0.1 degrees C. The resulting change in voltage, should it be large or small?
So that if there is change in 0.01, then we can configure that.
Yes, absolutely. I would like this to be large enough to be measurable. If the initial voltage was 10 volts, and if it changes to 10.00001 volt, that would not be easy to measure. But if it changes to 10.1 volt, that is much easier to measure. I can measure this also, no doubt. It will just take me a much more expensive voltmeter, the reading of which goes all the way to the 4th decimal, right? Instead, if I need, all I need is a change in the first decimal, that voltmeter is much cheaper and easier for me to use. I can even do it using a handheld voltmeter perhaps, right? So I am interested in increasing the value of delta V as much as I can. What do I need for that? I need alpha to be large, I need I to be large, and I need R naught to be large. Alpha is not in my hands. Alpha is a property of the material, right? I can perhaps go and look at candidate materials to design this. Let's do that real quick. It's a useful exercise. So thermal coefficient of resistance of different materials. Let me see if I can find a table. Table. This is a good one. Is it easily visible in the back? So what do we see here? First of all, the temperature coefficients are very low. The units, it doesn't give you a unit, it does, per degree Celsius. So every degree Celsius, the resistance of nickel changes by about 0.6%. Nickel that had a resistance of 1 ohm at this temperature, 1 degree C later will have a resistance of 1.0059 ohms. It's a very It's a very small effect, right? But nevertheless, there are some materials that have reasonably high temperature coefficient of resistance. Nickel being one of them, iron being one of them, and so on. I want to stay away from these guys. And by the way, these alloys that have extremely low temperature coefficient are designed that way. They put the right proportion of the mixture, whatever their constituents are, in order to make sure that their resistance does not change with time, because with temperature, because those are used in heating elements, and you don't want the amount of heating happening in the element to itself change as it gets hotter and hotter. In fact, the same thermal runaway problem, right? If this temperature coefficient of resistance is very high, then what will happen is it gets hot, its resistance increases, so it generates even more heat, because of which it will get even hotter and so on, right? That is the reason why these numbers are designed to be so low. But anyway, in order to design my temperature sensor, I would like a high value of alpha, and so nickel or iron are probably good candidate materials for that uh, for that um, um, sensor. In addition, the other thing that I can think of is I, the current. This tells me that I would like to have as high a current as possible, because the larger the current, keeping everything else the same, the larger will be the voltage difference produced, the change in voltage, and it will be easy for me to measure it, right? Should I use a very high current?
Increase the temperature of the
Yeah, yeah. The problem with using a very high current is that if I send a large amount of current through this sensor is a resistor after all, it will generate its own heat.
it will short also.
It won't short. Why will it short?
Generally, in resistors, when temperature become high, then the resistance properties lost. They lost.
Sure. So I'm not sending a ton of current, right? I'm not sending an unrealistically large amount of current. But nevertheless, at large currents, this resistor will generate its own heat. And so the local temperature that I want to measure here will get affected by the sensor itself. It's like I am trying to measure something and I am changing it in the very act of measuring, which is what I don't want to do. I want my measurement to be as passive as possible. Okay? They say that even the act of looking at something changes it. Why? Because when we look at something, we shine light on it, we are shining photons on it. A photon is going to go and hit the thing that I'm trying to measure, and it will not be the same thing ever again. Right? It is impossible to measure something completely passively. All we can do is to try and minimize our impact on that thing that we're trying to measure. So typically here, the way we think of it is that I am going to use the minimum possible I current that gives me just the amount of change in voltage that is measurable with my instruments. I have an instrument, it reads voltage to the second decimal. I will only send that much current which produces a change in voltage to the second decimal. If it produces a change in voltage to the first decimal, I'm sending too much current. I don't need that much. So I'll slow down on the current in order to get a more reasonable change in voltage. This phenomena is called self-heating. And I want to minimize self-heating. Okay? Now, you went to that table that I showed, you picked up the value of alpha from there, you know your initial resistance, you stick it in here, and you find out change in voltage, right? And back calculating, you find out the change in temperature. That is typically actually not how it is done. Typically, for any temperature sensor, I'm talking about all of this in the context of resistances, but this is true in general. In general, for temperature measurement devices, we have to always carry out a calibration. What is a calibration? It's an experiment done in advance of the real experiment to sort of teach the sensor what to expect. Or, in other words, if I flip it on its head, to teach ourselves how to interpret the output of the sensor. So, for example, if I have a temperature measurement device and I want to use it to measure a temperature in the range of 20 degrees C to 50 degrees C, then even before I start taking my measurements, I need to expose it to known temperatures of 20 degrees C, 25 degrees C, 30 degrees C, 35 degrees C, and so on, and at each of those known temperatures, I want to measure the voltage that it is producing. So in other words, I want to create a plot of voltage versus time. At 25 degrees C, I read a voltage. Then I repeat this measurement at say 27 degrees C, and I repeat the measurement and I get this number. I run this calibration at a number of data points, and I have been able to get what is known as the calibration curve. Why is this calibration curve important to me? Because this calibration curve is my key to converting any future measurements of voltage into temperature. Right? Having taken these measurements, now I am confident that if I run my actual measurement and if the voltage turns out to be this, then the corresponding temperature is this much. You know what I'm saying? The quality or the uncertainty of my actual measurement depends critically on the quality of my calibration. I cannot measure any more accurately than the accuracy of my calibration. If I calibrate it only at a few points, I calibrate it at 25, then at 30, then at 35, and then at 40, then I cannot report the temperature measured to be 26.3 degrees Celsius. My calibration was never as accurate to be able to tease out the first decimal here. I also cannot use it to measure a temperature of 18 degrees Celsius, because 18 degrees Celsius was never included in the range in which I measured the temperature during calibration. Okay? And the big challenge with calibration is that it requires me to provide a well-known temperature of 20, 30, 40, etc. degrees Celsius. Whereas, why did I start this process in the first place? I started this process in order to measure a temperature, right? So essentially the point is that in order to measure something, I need to calibrate, for which I need well-known sources of that thing itself. I need to have a body at 25 degrees Celsius, and then I need to have another body at 30 degrees Celsius and 35 and 40 and so on. In other words, before I go and measure the temperature of this body, I need to have a hot plate whose temperature I can control and whose temperature I can measure with great confidence. Then I will take my sensor, I will stick it to this hot plate, I will set the hot plate at 25, measure the resistance or the voltage, set it at 30, measure the voltage, set it at 35, measure the voltage, and so on, and thus create a calibration curve like this. And then, having created the calibration curve, I can now come here and take my actual measurement. There is no point of going directly and taking a measurement unless I have a calibration. Oftentimes, when you buy this sensor, the manufacturer will provide you a calibration. They will give you this chart that I drew in the next slide, or they'll provide you an equation between the voltage and temperature. But if you are a systematic, if you want to stay in control as an experimentalist, if you're very particular, you will carry out a calibration yourself. You will not depend on what the manufacturer is telling you. Of course, it becomes challenging because I said that I need to have a hot plate with a very well-known temperature in the first place. How do I know the temperature of the hot plate is correct? Because the manufacturer has calibrated that hot plate against something else in their labs. And how are they confident that they have done it correctly? because their calibration source has in turn been calibrated against something better. In fact, you can take this chain all the way back to some very well known standards of temperature that NIST, the National Institute of Standards and Technology in the US, maintains. NIST maintains standards of length, standards of temperature, and standards of all kinds of other things that we need to measure. So somewhere in Paris or wherever, there is a bar that has a length of exactly 1 meters. You can use that bar to calibrate a scale. That scale can be used to calibrate other scales. And strictly speaking, the scale that you use in your lab should be traceable all the way back to that well-known standard 1 meter rod. That entire tracing back is probably too much to expect. But at the very least, you should do step number 1, which is that you have a good quality hot plate, perhaps brand new, from a good manufacturer, and you trust it, right? You carry out your calibration at multiple temperatures on that hot plate. And then you have this calibration chart, which can be used for good accurate measurement of temperature. Does that make sense? Any questions? How do we calibrate a thermocouple? Well, what is a thermocouple to start with? A thermocouple is a device which comprises 2 different metals in wire form that are welded to each other at the 2 ends. And the property is that certain pairs of materials, if there is a temperature difference across, then that causes a voltage difference between the 2 ends. So you sit there, measure the voltage difference. If these two are exactly at the same temperature, there is no voltage generated. But now if this thing begins to heat up, you've taken this thermocouple and you've attached it, one end of the thermocouple is attached to some surface. The 2 metal wires are coming out. As this thermocouple bead gets hotter and hotter, a potential difference is produced. And there is a linear relationship between delta V and delta T. So as the temperature difference changes, the voltage changes as well. It's a linear relationship, and in order to be able to have confidence in the thermocouple measurements, you need to derive this calibration plot yourself. You need to take your thermocouple, stick it to a hot plate, and then slowly increase the temperature of the hot plate. At multiple temperatures, allow steady state to reach, and at that steady state measure the voltage difference produced by that temperature. And you run it at multiple temperatures, closely spaced intervals, and you get this plot. Once you have this plot, then you take your thermocouple out and you can go wherever you want and measure a voltage. Suppose you measure this voltage, then this plot tells you that the temperature must have been that. You know what I'm saying? In principle, this curve can be obtained only by 2 points. In principle, you can take one measurement here and one measurement here and join the two and you are done. But really the accuracy of that line gets better and better if you have more and more points through which you can fit that straight line. Even small, if you have only 2 data points, even small errors in these 2 data points can cause your line to shift dramatically. Whereas if you have a large number of data points, then small changes in one of them does not really change your line dramatically. That is the reason why it is recommended to calibrate at a large number of data points before you finalize your calibration curve. Yes.
and put it into the ice.
Yes.
And the temperature, whatever temperature is coming,
Is said to be 0 degrees C. Yes. And on the other hand, you do it with boiling water. Yes. Unfortunately, there are not a lot of other standards between these two temperatures, right? So, excuse me, in the lack of anything else, you use those two to determine this curve. And what can you do? But if you have a good hot plate, then it's never a bad idea to calibrate it at multiple points with the hot plate as well. Question?
Actually, as you were saying that using this interval of 5 degrees centigrade over here,
Hmm.
and are we sure that this 26.3 degrees centigrade is okay or not? Like, what should be the minimum voltage range that we need to capture, like for 20 degrees centigrade of temperature change?
Yes, so are you asking me, in order to get this type of accuracy, at how many points do I need to do the calibration? I would say that if you are going down to the first decimal point, then your calibration should also have been done with plus 0.1 degrees C. So I'm asking too much here, but you should be doing your calibration at 25.0, 25.1, 25.2, and so on degrees Celsius. Okay, most people don't do that much, you know. um, I think that if you're going down to 0.1 degrees C, it is perhaps okay to measure at 25, 26, 27, 28, 29 and so on. Sometimes we do it the right way and sometimes we are in a hurry.
The experimentalist will always make many senses to do calibrate.
Yeah, but calibration is a holy thing, you know. You cannot proceed forward without a good calibration.
With large temperature range that we are
Yeah, exactly. If you're doing measurements at high temperatures from room temperature to 500 degrees C, you cannot calibrate with plus minus 0.1, right? But then, to be fair, for high temperature gases, you never also report the temperature to be 750.2 degrees C. 750 is good enough, right? Sometimes even accuracy of plus or minus 10 degrees C is enough, right? At that temperature, does it really matter if the gas is at 740 or 750? It doesn't, right? So in that sense, in that range, you can probably calibrate every 10 degrees C or every 20 degrees. I think the general point that I'm trying to make here is that measuring something is very easy. All that it takes to take this measurement on this surface that we talked about is that you stick it in there, pass a current, measure a voltage, and you're done, right? But in order to ensure the quality of that measurement, it takes a lot of background work and effort. Before you even go to the lab, you need to think hard about it. There are a lot of choices to make. What material should I have? What current should I pass? Etc. etc. You go to the omega.com website and they will throw you 100 different temperature sensors. Which one do I choose? How do I attach it there? These are all thoughts that you need to plan in advance. You don't want to just show up and attach it, you know, with a stapler or something like that, the first thing that comes in your hand, and then just take a measurement and go away. You will never have confidence. You will never be able to convince others about the accuracy of your measurements. In your presentations, if you show the calibration plot and if those points are very closely spaced, done. People will never question anything else that is going on in your measurements. If on the other hand you just show the temperature measurement, and especially if you say that my temperature was measured to be 26.329 degrees Celsius, if you report that, that is what sets up a lot of alarm bells. If somebody is claiming to me that he or she measured the temperature to be 26.329 degrees C, then please show me how you're so confident as to go up to the third decimal. Maybe you are, but I need to see. Before I'm convinced that the temperature was as accurate as that, I need to see evidence that it can indeed be measured that accurately. I would much rather see somebody say that the temperature I measured was 26 plus or minus 1 degree C. Remember the thing about those who know that they don't know. At least this person knows that he or she does not know. Oftentimes that is enough. Okay? Short discussion today. I'll probably finish here since we are all tired. But I just wanted to communicate the importance of putting a thought process behind measurements. I can't just show up and take a measurement. I have to design it well. I have to think hard about it. I have to make choices. Consciously I have to choose the right things in order to ensure the success of my measurements. All right? We'll stop here. It's been a long day. Thank you so much for still being here. Tomorrow is half the day. Good news. And Dr. Tyagi's already said a few things about the exam. So have a good restful night. And I'll see you again tomorrow morning. Okay? Thanks again.